15-minute talk by Khomenko, also from the Khomenko Astronomical Center. Vadim is unfortunate enough to have me as an advisor, so anything good you hear is Vadim, so anything you disagree with is probably due to my bad suggestions. Please, Vadim.
Yes, thank you. So my talk is about waves and instabilities in the differential rotating neutron stars. And the aims of this project were to perturb two fluid equation for the neutron stars, and two fluids here are the charged fluid that is composed of the protons and electrons coupled together by the electromagnetic interaction, and the neutron superfluid. And another aim is to find a new modes of oscillation when the background flow is included in our calculations. So we used the plane wave analysis, and background flow here is a difference between the velocities of the superfluid and normal component. And to analyze the associated timescales of instability growths, both analytically and numerically. So the starting point here is multi-fluid equation of motion. That is here with mutual friction force on the right-hand side and a lot of terms on the left-hand side, like fluid rotation, chemical potential, and gravitational potential. And also we need momentum equation and the continuity equation. Here x and y label the fluid, so it's again normal fluid or superfluid. And IJK are running indices that label the coordinates. And of course, we also need some mutual friction force. So we used two different approaches here, or equations. This one is for the laminar flow and straight vortex array, and this one is the Gorton-Milling mutual friction. So in majority of cases, we use this equation with the two terms for the that contains the conservative and non-conservative mutual friction. And of course, we also needed the link between the number of vortices and the rotational rate of the star, this one. And this equation also contains entrainment. And next we perturb the equations. This one is the continuity equation and its perturbed form. And here's the perturbed equation of motion. So it's pretty huge. And we also here we neglect only the perturbation of the gravitational potential. As for the perturbation of the right-hand side, it's very huge, but we it can be divided, say, by 4 different terms that has different physical meaning. For example, the part that corresponds to sound waves, the part that corresponds to the velocity difference between the components, the part that corresponds to the change of number of vortices, and the one that corresponds to the change of the vortex vorticity vector. And this plane wave analysis is carried out by inserting these quantities. Here we have 6 independent velocities for two components and the perturbation of density. When this is inserted into the continuity equation, we arrive at this form. We also need the thermodynamical inputs, so we treat our system as the one at 0 temperature, and it's homogeneous system. So energy functional contain the chemical potential and the parts that correspond to the superfluid, this one. And the perturbation of chemical potential can be divided by 3 terms. And again, each term has physical meaning. For example, we have sound waves squared chemical potential, and this term is a complicated one. It contains entrainment and derivative of entrainment with respect to the density, but we don't use this because it's highly unknown. And so the final perturbed linearized equation of motion have this form, and with right-hand side is perturbation of the mutual friction force that has interesting form. So now we can find the dispersion relation. So what we need to do is to equate determinant to 0, and in general we have a system of 6/6 equations for unknown ground velocities, and also we have a lot of different parameters. So in numerical calculations we can include a lot of them to see the results, while in other cases, so we have a lot of different single cases to show. And so if the imaginary part is present in the dispersion relations, this means that we have unstable modes or damping of wave in time depending on the sign of the imaginary part. So first simple results, well-known sound waves and related oscillations. So these are sound waves that operates in proton and neutron fluids. They are decoupled. If we include the relative flow, we write this equation. So sound wave in neutron component is modified by the relative flow, while proton sound waves is not modified. This is because we choose our coordinate system to be locked on the proton component. And modification due to the entrainment is here, but we expand with respect to the small entrainment. And it looks like this. Another simple modification if we include also chemical coupling and sound waves. For this small expansion in the chemical coupling, this 4 waves here. Next, again, stable modes of oscillations is when we include rotation in our calculations. So it's for the inertial waves, and these are ordinary inertial waves, and the one modified by the background flow. We can also include the entrainment, and it has this simple form, or sound waves modified by the rotation here. And also we can include another parameters, but they're not very interesting because all of these oscillations are stable. A more interesting result is when we include the mutual friction. So here can be 2 regimes. I'll start with the weak drag regime. So if the induced drag is weak or the drag parameter is much lesser than 1, this regime is called weak drag regime. And in the case of strong drag regimes, one drag parameter is much bigger than 1. So in the weak drag regime, the conservative mutual friction is neglected, and we take into account only B, not B prime. And in this case, you write this known result when the inertial waves are modified by the dumped by the mutual friction in this weak drag regime. And you also may include, you can include an entrainment, and this results doesn't differ very much from the previous one. And note on this is that we use the Cartesian coordinate system, or it can be recasted, say, in the polar coordinate system, and this analysis is local because it's plane wave analysis. Next, we start including the background flow. First, we wanted to restore the Dunlop-Globerson instability. So the background flow operates in that direction, and here we have, say, 2 cases, 1 fluid case and 2 fluid case. The well-known one is the 1 fluid case, and it's obtained in a clumped proton setup, but we restore it by taking this fraction of densities to be equal to 0, and physically this means that the mutual friction force doesn't act on the normal fluid and acts only on a superfluid. Well, the more complicated case is this one when the mutual friction force acts on both of components. So here we have an instability, minus sign corresponds to this instability. And for the 2 fluid case, equations are much bigger, but if we take small entrainment or expand with respect to small entrainment, we arrive at the 1 fluid result. Result means that there is no difference between these setups if the entrainment is small. And the entrainment parameter is very important for the neutron stars, especially if you consider the core. And we may obtain the similar results for the expansion when we consider the strong drag regime, or when we neglect this B but take into account B prime. And also there's also some results if you neglect almost everything except all CB and B prime, and these results are unknown and they are simple. Next sort of new result and very interesting one is when we consider background flow in x direction. X direction here is a direction that lies in a plane perpendicular to the vortex line vorticity, and vortex line vorticity here is aligned with rotational axis of a star. And we start with, with one fluid setup and arrive at this dispersion relation, and it seems that there is an instability, and when we find this condition for instability to develop, but we can small expand with respect to the velocities and arrive at this simple result. And we can also make a third order expansion, and there appear a new dependence on a wave factor in y direction, meaning that this instability acts not only in a simple x direction, but in a plane that is perpendicular to the rotational axis of a star. And also they make this similar instability in a strong drag regime, and it's a condition for this instability to develop. The next step, since we have a lot of different parameters, we did some numerical calculations, and these are two examples of these numerical calculations. And on this figure, the pinot vortex scenario is shown is when the velocity is aligned with that axis, and we consider the wave vector parallel to that axis as well. A lot of different setups are shown here. For example, standard case when we include rotation, entrainment, and so on. And also we consider stuff with the core when the entrainment is positive and small. And this one is for the maximum drag scenario. And what can be seen here is there is also instabilities that acts on very short time scales, and especially core instability when the entrainment may change sign. So this is very interesting because we can also always find this instability with very short time scales that are interesting for us. And conclusions. So we show the existence of different stable and unstable modes of oscillations, and we were interested in especially in unstable modes. And also we did some analytical and numerical calculations and found a new two-stream instability when the background flow oscillates acts in the direction in a plane perpendicular to the rotational axis of the star. And also it shows that the core case may always be unstable because entrainment change sign, and we did some calculations connected with Gorton mutual friction, and showed the inertial modes are always stable for J mutual friction, unlike the case of HBVK mutual friction. Thank you.
Left corner. Does it mean that instabilities are very efficient then? I mean, gamma is very so the time scale is very short.
Yeah.
Right. So which means that the damping or the growth is the rate is very high, which means that they almost instantly grow up and change the picture.
Yeah, so those ones are unstable.
So what I mean, what does it then mean for the model if those instabilities at low momentum are so efficient and so quickly growing?
You want to answer that one? It's an instability, right? So this is on a larger. This is a fluid sort of hydrodynamical model, right? So you have some modes going unstable. You may expect that then it'll disrupt the vortex array.
I mean, in the quantum model, you have two superfluids altogether, right? If you have such a strong instability on a very, very short time scale. I mean, do you get out of the hydro picture, or does it still stay everything valid? Because you have a gradient expansion to go into the hydro picture, right?
Right, so you would expect that you disrupt this somehow, then you can't really see with this model where you end up. You just see that there's a fast growing instability. It depends on this background velocity and entrainment things, but other than see that it develops quickly, then you can't. At that point, you sort of lose the picture, so you expect that possibly you've disrupted the vortex array. Comes over, you don't know, but you can't model that in state with this, so you just know that it happens, but you can't tell you this way what state you've gone to. Other than it's interesting that, I'm sure that this is done with the kind of standard straight vortex neutral friction, sort of HPBK one, and then it goes unstable quickly, but then you go to the, if you take something isotropic, then this is what you might expect, and then you sort of settle in some state, and then you sit there for a while until it's maybe the turbulence is decayed, and then you start pulling up that picture again.
Yeah, but it would be a different flow regime. I mean, if we disrupt the vortex array as this mutual friction. And, we should use some another force now.
Well, yeah, someone has to go and solve the problem.
How do you get the values for the entrainment coefficients that you use here?
But these values are from the paper of Shamal's
That's
paper.
for the crust, right? And then you took.
So this is based on overall phenomenology and then trying to figure out what entrainment parameter. There's no way of estimating from microscopic that you know.
I see. No, there's not.
The Shamal's would be microscopic, right?
Yeah. And also for
apart from
I mean, it's a microscopic formulation, but the entrainment's not calculated from
Yes.
microscopic.
why? Isn't it just JJ?
I mean, you can put an entrainment term in the functional, and you have to fit that.
Oh, yeah.
Right.
So, okay.
Yeah, the instability when the flow is perpendicular to the vorticity, is it any different from qualitatively from what happens in the counterflow turbulence, for instance, where the counterflow, essentially mutual friction, blows the vortex tangle, or even a slightly bent vortex line will eventually, with certain values of mutual friction coefficients, can be blown up and eventually reconnect and form a fully flashed vortex tangle. So is it any different qualitatively from that picture? Because this has been discussed a lot, especially in later, I think, in the helium-3 experiments, right, in Helsinki group, where they observed transition to turbulence depending on the temperature of the system. Because in helium-3, there's a lot of sensitivity in mutual friction coefficients to temperature, so we can actually observe that mutual friction drives this instability when obviously vorticity is it's rotating cryostat that we're looking at, if I remember correctly. So the vorticity is actually on the exits. So it's very similar to your setup. So is it any different from what you observed? Is it any different from the human picture? Because you said it was new mechanism. So
yeah, but I'm not sure if I can compare these cases because there is no temperature here, temperature dependent, and this is like different setup. But I
but you do have the coefficients B and B prime, which are exactly the same as the mutual friction coefficients.
The mathematics is completely similar.
Right.
Okay.
Slightly different, I guess, because instead it's your normal component is not a thermal one here, but it's still another component. So I guess qualitatively.
It's
qualitative.
Although here this is hydro, right? So we don't actually model the vortices, so we can't. It's like on an average sense in your box. So I mean, qualitatively, I would guess
it's the same
thing, but then I can't.
Because it would be interesting to compare, because this problem was looked at by the Helsinki group, and Bolovic, I think, also wrote some theory possibly. So maybe it's interesting to compare when the transition to turbulence happens in terms of their parameters, whether that relates to what you see in terms of being prime parameters.
But you can think of this work as a study of the instabilities of the HPBK equations just with another language that is equivalent.
Yeah. You have to be careful. I guess what the parameters actually are.
Yeah.
But yeah, I think that's interesting. We should definitely look at it.
So the thing that changes is the interpretation of the normal component.
Sure, I understand. I understand the dynamic of this. Can you go to the next slide?
And the range of the parameters.
No, the final, sorry, the conclusion slide. Yeah, to say find a new unstable mode that acts when flows perpendicular to the vortex. So I wonder how much new is it?
Right, yeah, I guess it's in this setup, but
That's what got me a bit confused. So I'd like
because I
to
guess-
learn if it's really different. Then I'd like to learn, what the difference is.
yeah, so maybe it's actually, I mean, I guess it sounds as if qualitatively it's that. So I guess you can use it in this setup for the neutron star, including this background flow. This is new, but I guess you're right that it's qualitatively the same as having counterflow across
Right.
it's the rotation axis. So yeah, we should look into that because that's a good connection to make. So it's different from the sort of diversity thing.
Sure.
But what you're saying sounds qualitatively the same picture. So yeah, we should look at that.
But in that case, the coefficients change as a function of the flow when you start creating turbulence and stuff. The neutral
As a
friction,
function
I
of
think.
temperature, you're saying, right?
Well,
But just as a function of temperature. you're
Just
saying.
as formally they do change at the theoretical level, but there are logarithmic corrections which we neglect. So yeah.
But then the temperature, yeah. Think of that as setting off.
Yeah.
Interpreted in terms of our ratios between the fluids.
Yeah, because it seems like that helium experiment essentially models what you're predicting here with mutual friction due to thermal components.
Yeah.
Fluid, so.
I guess the different thing here is that in different regions you can have to change the sign of the entrainment. That seems to be the relevant thing for the core, which
Oh, I see.
kind of new things that which you can't. I think you can't switch it. Of course, you think of a clever way to change the entrainment in that.
If I can make a last comment, probably Vadim used the word new just because there is a previous paper by Niels and Sidery and other people where they already discussed this kind of instability, especially the Glaberson-Donnelly one, when you have the leg parallel to the vortex array. So it's new just because this setting where the vortex array and the leg are orthogonal wasn't discussed in.
I think the main new thing, I mean, it's nice that you make a comment just to blame the else.
Yeah.
I think the main.
Not in this sense.
I cannot entirely agree with that, but I guess the new thing was looking at what happens when you change the disentrainment, because it's going to be large positive in the cross, negative in the core.
Right. So here, in addition to the mutual friction with the normal component, we also have entrainment, which could potentially modify the picture. Potentially qualitative. Right. So is it not driven by mutual friction then?
It's driven by mutual friction, but then the entrainment plays a role.
Right.
So
is it like considering mutual friction between neutron and proton superfluid?
Neutrons and protons, yes, I guess in the core of protons can be superfluid or superconducting.
Superfluid.
Or whatever. But then we don't have proton vortices in there, so they would show up in the mutual friction coefficients.
Just to say, I totally agree with describing anything that I didn't do as new. It's perfectly okay with me. From now on, anybody's free to use this as a reference. That just means you have to check everything that I ever did.
But I guess
Make
it
sure
means
that
that a lot of these.
Can we just ask you?
Yeah, but I'm getting older. My memory is not.
Not something I guess.
And also
a lot of
there's a
people
couple
in
of-
this room actually work on different things. So So anything
Yeah.
they think of doing is.
And there's quite a lot of stuff I did that I don't really approve of myself. So
I guess if the discussion is taking this direction, we should probably stop.
We should.
Yeah.
But also-
Unless anybody actually has a question to ask, but doesn't relate to what Neil
Okay, I
said.
have a question.
Can I just
Yeah.
hopefully it's a quick one. So in this mechanism, what's the role of entrainment? How does it modify the picture? Or let's say qualitatively, if I switch it off or I increase it, how does instability respond to that?
Well, you have some, I don't know if you can see it from the expansion. I mean,
N is with no entrainment.
Okay.
C is with the entrainment with a reverse sign, which happens in the core, and A is the standard case in the crust. So where entrainment is negative, while C is with positive entrainment parameter. So
it modifies the timescales quite a lot.
Right. Okay.
So I guess you have additional coupling.
Right. Of course.
You still need the mutual friction to actually drive it, but then the way it responds is quite different.
I see. Okay. Yeah.
I have a question. So this counterflow instability, does it have a threshold of velocity? The counterflow when it sets in? Or?
If I remember correctly, it only depends on the mutual friction coefficients. It's a self in there's alpha and alpha prime, and what's relevant is the relation between them. It's I don't remember exactly. It's the ratio essentially of something like alpha minus alpha prime to alpha. You can show this that it's essentially from considering how much the vortex line is displaced during its, let's say it has some kind of curvature, then it has self-induced motion and motion that is caused by the track and the energy exchange with the normal component. And you just see that actually the curvature of the vortex line drops out of the estimate of when it becomes unstable. I mean, unstable meaning that it can loop on itself and create essentially self-cross and create the vortex ring, which will eventually collide with the rest of the vortex tangle and blow up instability. So that's essentially the criterion of the instability. So if essentially it does not depend on the velocity of rotation or on the velocity of the vortex line itself, which is determined by its curvature, but rather on the ratio of the mutual friction coefficients, on the ratio, relation between the mutual friction coefficients.
Right. So one of the two, I guess, is trying to.
So one of them, so if you have a vortex line, so one of them just, if you blow with the normal component at the vortex line, so one of them just tries to stretch it to extend the vortex ring, and also, and the other, it just kind of pushes it in the direction of the flow. And then there's a self-induced motion of the vortex line, so it just wants to twist on itself. And when you compare those effects, and you see that in some regimes, the mutual friction is not is too strong to actually allow the vortex line to loop on itself, and the system remains laminar.
Right.
But when it kind of gives essentially the initial push, and then the vortex line just continues by itself, self-induced motion, and then crosses itself, it uses the vortex ring, and that's the criterion. But yeah, but I think it was described somewhere very well. I'm reconstructing from memory. Physically it makes sense.
Okay, yeah.
So maybe 10 years ago or 15 years ago, helium-free experiment also came.
Okay. Right, if there's any questions?